All right. Well, again, thanks for joining in, and we're going to get started now on dry block temperature calibrators. So, first thing, a little housekeeping. Um, we're going to record this webinar. You're all going to be muted, and questions can be asked via the chat function at any time. And we'll have a question and answer session at the end of the seminar. We're going to share the presentation slides. They'll automatically be sent to all the attendees via email once we're done, and the recording will also be available on our website and our YouTube channel. So I am Scott Crone. I'm an area sales manager and a product manager. I've been in various roles for Amatec STC. I've been with the company for I'm real close to 29 years. I've got a BA from Eckerd College in Management Marketing and Management Information Systems. And my background comes from being a U.S. Navy veteran. I was an electronics technician, reactor operator on submarines. So our side duties beyond operating the reactor were performing calibration. So that's how I ended up in this world. And this is one of those industries that once you're in, it's very hard to get out of. So we're going to describe the construction, evolution, and practical use of dry block temperature calibrators. We're going to go through the basic design, some of the added features that are taking the dry block from just being a heat source up to a real true calibration instrument, how they should be used, some common misuses, and we'll talk about some basic measurement principles and devices as well, along with some additional heat sources that you might see in the marketplace. So let's just talk about temperature and thermal energy. Thermal energy, and this is going to be very important as we talk about some of the future topics in this seminar, but thermal energy seeks the easiest place to be, the least energy that it can. So what happens when two objects are near each other? They're going to seek to be at the same temperature. So they're going to transfer energy from one to the other until they get to an equilibrium temperature. And that thermal energy is measured in joules. Now, what we're going to talk about today is temperature. And temperature is that energy transfer from the hotter to the colder or colder to hotter instrument. And it's measure of the warmth or the coldness of the object. It's measured in Kelvin, Celsius, and Fahrenheit. So when we talk about temperature measurement, there's a lot of devices that you might know, but the big thing to remember is that everything seeks the same thermodynamic energy, and the sensor that you're going to use has an impact on the measurement. What's even more important is sensors only measure their own temperature. So you have to wait for those sensors to equalize, and I'll talk about that a little bit more in the future, but it's very important to understand that temperature, unlike, say, an electronic calibration or a pressure calibration, temperature takes time. You have to give it time to stabilize before you actually take a reading or take a measurement. So what you might see out in the field are liquid and glass thermometers with a reservoir of liquid. A bimetallic thermometer, where you've got two different types of metals that expand and contract at different rates, and they're connected at the end, and they twist, and they'll turn dial. You might see an RTD, resistance temperature detector. So what that basically means is you've got a metal that has a linear resistance coefficient. And for example, a PT100 means that it's a platinum element, 100 ohms at 0 degrees C. And those are characterized using fixed point cells. And I'll kind of hit fixed point cells a little later on very briefly. But RTDs are very, very common in this industry. They're very accurate and very stable. Thermocouples are two dissimilar metals that generate a voltage due to a temperature change. So there's all kinds of different combinations that are out there. Some of the more common might be a type K or a type J. And they use the Seebeck effect, and that basically means that they're going to generate a voltage as they are heated or cooled. And you have to reference that to a cold junction. So that's why cold junctions are very important in thermocouple measurement. Thermocouples are typically characterized, you might notice them by their color. Those colors vary based on where you're at. So what might be like, say, a type K thermocouple that's yellow in the US may not be that same color in the UK or in Europe or in Asia. One of the other sensors that's a little bit more prominent these days is a thermistor, and it's a semiconductor type of resistor, and it's either a ceramic or a polymer. It's limited range compared with an RTD or a thermocouple, but what they typically do is they're going to have a positive or negative temperature coefficient, and as temperature changes, they're going to conduct or not conduct. They're not so much used, excuse me, for a reading, but they're used to create functions within circuits. So with that, we've got to figure out how we're going to change the temperature on these things to get a reading out of them or get a calibration out of them. So temperature sources. So I spoke a little bit about fixed points, and this is a fixed point cell right here. The temperature sources are going to generate a temperature, and they may or may not be traceable. Now, a fixed point cell is a physical standard with elements in a specific state, and most of you have probably heard of a triple point of water cell where you've got vapor, liquid, and ice, and you characterize an RTD using that. Well, there's, I think, 11 different fixed point cells that are used to characterize an RTD through the ITS scale, ITS 90 moving into the ITS 10. And those are very expensive. They're not very portable, and they're only good for those fixed points. They're really used basically physical standards used for characterization of an RTD. Now, what we have seen out in some areas is you might see this, where somebody's using a cup with ice and water and calling that a 0 point. It's not uncommon. We see it out in the field a lot of times. It's a lot easier with a Yeti that they have now. Because those hold temperature for a little bit longer. But the problem is it's going to striate. You're going to get levels of different temperature within that cup, and you don't always know what impurities are in there. So it's not typically going to be an actual 0 point. So what some labs will do is they'll get an automated slurry, right, like that one, and it'll produce its own ice, and it'll spin, and it'll keep that slurry moving. So you do get that 0 point, and that's great for a 0 point, but it's only that 1 point, and it's only going to help you to basically characterize an RTD or check an RTD. It's not going to help you if, say, you need to calibrate a thermocouple over a different range. So what we see sometimes is we're going to see customers go out and use hot plates. Now, they're going to use a hot plate, and that hot plate is only good at that 1 point right where it touches the plate. And you can see that there's nothing really on that dial. It's just either hot or cold. So it's really not a traceable temperature. But again, it does get used. People do that, and they'll boil water, and they'll drop a thermometer in there and say, well, it's got to be 100 degrees C or it's got to be boiling. Well, that's great, except that you may not be at sea level. You may have impurities in the water. And it's only good right where you've got that 1 point of contact. It's also only good if you've got a traceable thermometer in there to reference it. One of the other technologies that used as a heat source is a sand bath. These use some exotic materials in a like a porous or a sand kind of consistency, and you'll stick the element in there, and they heat up to a certain point. Those were pretty common because they were a little bit easier to move than liquid baths. But the problem is they're very slow. It takes a lot of time to get from one temperature to another temperature and to let it stabilize. Once it's stable, it hangs on pretty well as long as you get the gradient and have a reference in there. But they do take a lot of time. What has become more common is a fluidized bath. So the fluidized bath, and they're typically circulating baths, they're going to move a fluid, sort of like a silicone or a cryogenic fluid, and they'll keep that moving, and you get good homogeneity. In the example that I've got there, you've got nice positioning of the sensors under test, but that isn't always the case. And the liquid is very expensive. You got to train people on how to use it, how to dispose of it. You're going to have to buy new fluid on a regular basis. And it's also a spill and a burn hazard. So what ends up happening is we've migrated to the dry block. The dry block is a great portable temperature source that's used for many industrial applications. And it has evolved over time to give us features that bring it even closer to some of the laboratory sources like the fluidized bath. The way it came about was it was basically a customer came to a sensor manufacturer and said, hey, we need something that's a little bit easier to use than a fluidized bath. And that's how the dry block came to be. So talking about basic design and operation. So dry blocks are extremely simple. When you think of it, there's not a lot of elements going on here. There's basically only 5 elements. I know there's 6 in the picture, but there's really only 5 elements to the dry block because the first element is the sensor under test. So you got a solid metal block with an interchangeable insert. You've got an internal RTD and reference sensor, heating and cooling elements, and a cooling fan. And that's pretty much it. Now, the controls on the cooling fan, the quality of the internal RTD, heating and cooling elements, and additional functions have been added over time and create a much more complex instrument. But this is the basic breakdown of it. It isn't anything overly complicated to understand. And when you look at it, how does it work? Well, basically, you enter a temperature, you put the sensor under test in the block, you set the temperature, and you get current flow. Now, current's going to flow basically in the heating elements or what we call the Peltier elements. So the heating elements are resistive heaters. Anything from ambient and above is typically going to use a resistive heater. Now, we get the question a lot of times, hey, can we get a dry block that goes from 0 to 500 degrees C? And that's not available. And the reason it's not available from any manufacturer is because if you look on the slide here, we've got number 2, Peltier elements. So Peltier elements are doped semiconductor material that when you flow current one way, they're exothermic or they heat up. When you flow current the other way, they're endothermic or they cool down. But those elements have limits. And if you continue to put the stress those on one end or the other, you're going to break down the barrier in the middle. And when you break down the barrier in the middle, they lose functionality. So there's limitations. Typically what you'll see in the available dry block market is anything that's going to cool below ambient is going to come to about 150 C positive. Now, there's a couple of outliers out there that go a little bit higher. We've got one that's going to 185, but that's pretty much the limitation. And that's why when customers ask or come to check on what is available, they're limited. And in a lot of times, they're going to need 2 blocks, one to cool and one to heat. So once you get the current flowing and you're getting a temperature change, the reference sensor supplies input to a comparator circuit. Now that might be an internal reference or an external reference. And I'll talk about external references a little bit later on. And they'll continue to work to match the reference and the set point. So that reference is going to continue to sense and provide input to a control circuit. And it's going to keep heating or cooling until it reaches a stable temperature. Once it gets to that temperature, it'll cycle around it till it stabilizes. And what you might hear is the cooling fan kick on and off. If you're going from a hot temperature to a cold temperature, you're going to hear it kick on very loudly. But once it starts to stabilize, it'll click on and off. And then as it's stable, it'll click on and off to control that temperature. And that's really it. I mean, there's nothing overly complex about how this works. So what are we looking at to calibrate in there? So the ideal sensor under test is going to be of moderate diameter. It's going to be round. Have a consistent diameter through the immersion length. So we want it to be the same diameter from top to bottom, if at all possible. Now we can address some special designs, and I'll talk about those a little later on. But ideally, you want it to be the same diameter, especially in the immersion area. It's going to bottom in the insert and extend slightly out of the top of the insert. We'll touch on this again a little bit further on, but you want it to be long enough to where when you set it in the dry block insert, it's going to stick out. It's going to have a sensing element located near the bottom of the sensor. Again, we'll talk about that a little bit, but you want that near the bottom because that's where the control circuitry is going to be in a single zone well. And you want it to be straight. Being curved or another shape is just not really suitable for a dry block application. So when we go back and talk about how that was designed, the initial dry blocks were designed by a sensor manufacturer. The customer was a shipboard company, and they were performing calibrations in an engine room. And because of my background, I can tell you that moving a wet bath around an engine room in a ship is just not the easiest thing in the world. So what they came and asked the manufacturer for was said, you make great sensors. Can you do something for us to help make it easier to calibrate? And they did. And the first calibrators, the reason they're called dry blocks is because they were actual blocks of metal, and the first ones heated up. They didn't really cool down, so they were checking warm temperatures only. And those things were basically heat sources. They performed as expected. They weren't seeking high accuracy, and they weren't looking for a lot of features. They were looking basically to set it at a set point and let it go. And when compared to a bath, it was faster heat up and cool down, wider temperature ranges. It was smaller size equipment to move around and much more portable, and no hot or hazardous fluids. So, you know, it minimized the burn hazard. It also minimized the spill hazard. Silicone can be very slippery, and taking that liquid out of play made it a lot safer for the technicians. Now, when you evolve it, what we've done, not just us as a manufacturer, but all manufacturers have had input into taking the dry blocks and moving them along from being a basic block of metal that heated and cooled to getting additional features and additional performance. So as technology progressed, we were able to give it better performance and better capabilities. And now it's viewed as a solution for certain lab applications and not just for industrial use. So other factors came into play, and as we started to grow the use of dry blocks, we had to consider stability and well homogeneity, axial and radial, axial being the top to bottom homogeneity and radial being the side to side. We had to talk about the loading effect. Loading effect is when you put something into the sensor. Remember I talked about sensors only sense what they're feeling. They're not really measuring anything else. And that energy transfers from one surface to another. So the loading effect is when you put a probe into a well or into an insert, you're going to see that there's an instability, and that instability is caused by those temperatures trying to equalize. As you put more sensors in the well, which is specifically what lab applications are trying to do with baths, they're trying to put more sensors at a time to increase efficiency. That loading effect is worse. So we had to come into different ways to address that kind of an effect, and basically comparing the dry block to a bath. So this is what the customers wanted, and here's how we embarked upon making it happen. Power supply stability. So the first thing we had to address was a lot of the industrial dry block applications were in areas where you had large machinery cycling on and off, such as in a power plant or in a steel mill. And what would happen is that when that grid power would cycle, it would cause instability in the dry block. When you cause instability, now you've got to wait for the block to come back to a stable temperature. And when it takes time to do that, you could end up with an endless cycle of things turning on and off and it going unstable. So we isolated the power supply and provided what's called main variance immunity. And main variance immunity is throughout our entire product line of blocks, and it compensates for those power fluctuations. So it maintains a steady energy flow to the dry block calibrator. It keeps that temperature stable, and once you achieve stability, it's going to be able to maintain it. And then we had to address radial homogeneity. So if you're going to put multiple probes in the block, you've got to have a bore-to-bore difference that's minimized as much as possible. So we do that through efficient well design. We look at airflow through the block. So the blocks aren't just solid pieces of metal now. They're machined, and they've got extensive heat transfer surfaces. The location of the reference and the location of the elements inside the well plays a factor in how much we can maintain radial homogeneity. And then we've got better well control. So circuitry has come about and become better that allows us to get better control and better feedback between the references and the control circuits. And then we have efficient insert design and proper materials, which allows for consistent heat transfer. So a lot of those different materials are available now. We've been able to evaluate them, and I'll talk about those a little bit more in the future slides. So let's talk about block evolution. So it's energized to maximize heat transfer airflow. So I don't know how many of you are familiar with electronics such as stereos and amplifiers and things like that, but those heat sinks that are on the back allow for efficient heat transfer. So what you do is you create more surface area for better heat transfer. And because we have better machining technologies, we can do much more complex designs. So if you look into a dry block today, If you look in through the top or look at the bottom, that block is going to have several different surfaces and airflow patterns that go through it. We can use different composites and alloys, so we can go and seek out materials that are going to allow us to maintain better stability, but also to transfer heat as needed. And we've got new and improved heating and cooling elements that are available to us. So even the Peltier elements and the resistive heating elements are of better design and a better quality. We also have better RTDs that are available to sense, or thermocouples actually, for the high temps that are able to sense and control that. We have analysis software, so we can model a design and see if it's going to perform as we think that it's going to perform. We can calculate the efficiency, and we can model the homogeneity. And because of all these evolutions in materials and machining, we've also reduced the weight of the dry block. So even a reference level dry block today is as light or even lighter in many cases than a basic industrial dry block was 20 or 30 years ago. Now, along with that, we had to work with the inserts. So with the inserts, we've engineered them to maximize that heat transfer. Again, new composites and alloys, but improved finished and treatments. So the surface areas on the inserts maintain longer. They don't corrode as quickly, or you don't build up a layer of corrosion or a layer of chemical barrier. Again, with the machining, so with new techniques and more complex machining, we can achieve a smaller tolerance. So we can have a smaller tolerance, not just between your sensor and the bores in the dry block, but also between the insert and the block itself, which again allows for better stability and faster heat transfer. And we're going to use that same modeling software to achieve homogeneity and efficiency within the design. That was radial. So now when we talk about, yes, so Miguel, that does actually affect the stability of the insert. And what we do is when we look at different designs, and I'll talk about this a little bit in the future, but we do actually take that into account, especially when we're talking about blocks that are designed for multiple insert use. And that's a great question. It kind of really leads me into what we're going to talk about here in just a few slides. So axial homogeneity is the top to bottom difference, and this effect is minimized through well zone control. So we've got a couple of different options. We've got single zone, passive dual zone, active dual zone, and then a new patented technology that we've employed in our reference temperature calibrators called dynamic load compensation. So single zone control is basically the traditional dry block technology. This is going to be in your industrial dry blocks. There is no temperature gradient control, and several factors determine the gradient. So I talked a little bit about loading when you put sensors in and take them out of the well. So what happens is, as that temperature effect or as it's seeking an equilibrium, the other thing that happens is it's seeking an equilibrium outside of the block. So that heat energy, whether it's cold or hot, is seeking to go to atmospheric temperature as quickly as possible. So you've got it in the block, but you've got a portion that sticks up above the block. And any kind of airflow or anything like that is going to allow that heat to flow out of the block through the sensor under test into the ambient. So if you look at the curve that we've got here, when it's not loaded, it's a very small difference from the top to the bottom of the well. But when we load that down, you can see the other curve loaded shift inside, the yellow curve, and it becomes a much bigger gradient. So what we're going to see that we have to do is we're going to have to insulate the sensor under test and minimize that airflow or that heat transfer out of the insert. So to compensate for that, we developed passive dual zone control. Now, we no longer use this technology, but it's a good technology to understand. And basically what we did is we took the top portion where we saw that heat loss, and we put a second set of elements up there. And what it was a fixed energy ratio, and we shifted some of the energy from the basic main zone at the bottom up to the top to just keep a little bit of energy up there and keep it from going away. Now that basically took away some of the need for insulation. It gave us good lower zone homogeneity. And because of that loading question that you just asked, this will allow us to take care of multiple sensors, because as you add more sensors, that curve shifts even more and more away from true because of the loading effect. You've got more things trying to reach an equilibrium in the well. So this allowed us to calibrate multiple sensors under test, and it gave us a smaller vertical gradient. And it's great technology, but there's better. And the better is active dual zone. So instead of just saying, hey, we're going to take 20% of the energy from the circuit and put it up to the top, we're actually going to put an intelligent energy distribution circuit up top and allow it to measure and compensate on its own. So what active dual zone control does is it takes, you've got the main zone and then you've got the upper zone, but the upper zone is operating on its own. It's not taking part of the energy from any of the other zone. It's basically measuring and saying, yeah, I really need some energy up here to compensate for the energy we're losing to ambient. And it's a continuous axial measurement. It allows for not just the multiple probes, but it allows us to consider calibrating short sensors under test because we do have that control up there. And it minimizes the vertical gradient. And this is a great technology. But we moved on from there and added one more element in our reference level calibrators, and it's dynamic load compensation. Now, the way I like to think of this is dual zone or even triple zone, because we've added triple zone to the heating dry blocks. So because they're a deeper well, we actually have 3 zones in those. But the dual zone or triple zone works in the block, and I like to call that the course adjust. So it's taking that comparison, it's moving the energy around. Well, the DLC works in the insert, and it's what I call the fine adjust. So what it does is it takes those loading effects and it compensates for that. So as you're putting sensors in or taking sensors out, that instability is going to show. It's going to measure that difference and make a change in the loading. It's going to make fine adjustments throughout the axial zones and adjust the dry block back to stability. We can get down to 5 thousandths of a degree stability using this technology. And again, it is patented. So what does it do? Well, DLC is accomplished with an extra sensor in the insert. It's a high accuracy thermocouple, so that's it on the right side of the image there, and it's a dual element thermocouple. So we sense at the bottom, and then we sense at about 60 millimeters from the bottom, because most sensors, that's the thermosensitive length of nearly all of them. And it's going to read the difference in the 2 levels. So it will read those differences and adjust temperature. It's going to adjust energy to the different zones to adjust the temperature difference to 0. And it's not just making that adjustment in the background. You can actually see it on the display. So that information is there for the user so that you know when things are the most stable as possible that you can get your reading. And this is what that heat curve looks like. So it's kind of flipped around from the previous picture, but you can see that when the DLC function is on, that's the green line in the graph, and the red line is when it's off. So you can see how different the axial temperature is for those different sensors. So those 3 different sensors in the well have different depths where the sensing elements are, and there's a slight change, and it's up to 5 thousandths of a degree between the one at the lower and the one in the upper. And that's based on the axial gradient going from bottom up to about 60 mils in the, up in the range. If you look at the green curve, there's virtually no change between those 2 up to that level. And it controls that heat energy to maintain it that way. And there's a full white paper available on our website that talks about exactly how the DLC works. It provides you with all the uncertainty calculations to show exactly how, first of all, how we achieve this curve, but second of all, how we know that this technology works. External references. So one other thing that has come about is using an external reference. Now, with industrial level dry blocks and earlier with the older design level dry blocks, what customers would tend to do is they would say, well, I need a higher accuracy reference to compare my readings to than you can show on the display. And they would use an external reference and a different handheld readout and things for that. Well, what we've done is we've incorporated the ability to read external sensors and read it right on the block. So you can use the coefficients for that specific sensor. So instead of using a general curve fit for the RTD, like you would do for the installed sensors, it uses the actual curve fit for that specific sensor. And what that does is that allows it to get a much more accurate reading, and it's sometimes 3 times more accurate than the sensors that are installed in the block. You can position that external reference to the closest position of the sensor under test. So this is the other tool that allows us to do short sensors within a dry block. And it's possible to operate using this input. So we use a mode called set follows true. And set follows true allows us to say, nope, I want you to read the internal sensor, but disregard that reading and use the external sensor only. So what you're getting is the most accurate temperature in the block or in the insert closest to the sensor under test. Now, this isn't always necessary. So a lot of customers may not need a reference, an external reference. The block itself may be accurate enough, but the application may need it, and it's there and it's available. The other thing that the external reference allows us to do in a single zone dry block, it'll allow you to perform a self-calibration. So the routine is installed on our CTC series dry blocks to where basically you drop the reference sensor in, plug it in, and put it into a calibration routine. It does a calibration on its own. And after that, you keep the block on site and you send the sensor out for calibration. So that's a nice feature, but it really is only available on the single zone dry blocks. If you've got a dual zone, that becomes a much more complex task because you've got to calibrate each zone in the block. Now, beyond all the internal features that you can't see, well, you can see the reference probe and the DLC probe, but you can't really see what they're doing. We actually added in some automation. So what customers said was, these are great. What else can you do for us? And a lot of these are things that BAS really can't do. So we can do self-checks. We do self-check every time you start up one of the instruments. We can do auto-stepping. Auto-stepping means I need to go through this series of temperatures, and I want you to go from A to B and hold for 10 minutes, go to B to C, hold 10 minutes, and you can set up all those temperatures and then let the dry block go on its own. And this is even available on the most basic level dry blocks. An example application for that might be you've got to read that sensor at some other place in a plant. So you'll go to that remote control panel. You can let the dry block go by its own, and it's going to run through those temperatures, and you'll be able to take your readings. Ramping is going up and down through temperatures at a specific rate, which follows on to automatic switch testing. So automatic switch tests are probably one of the most valuable tools available on dry blocks in the industrial level dry block. Time is money. And again, going back to what we talked about very early on in this presentation, temperature takes time. So if you've got a technician out on station, one of the things that they might need to do, say in a power plant turnaround, is to check temperature switches. Well, the old way to do that, the way that I did it when I was in the Navy, was you put the heat source on the sensor and you had a multimeter in your hand and you watched for that multimeter to change state, for the switch to change state on the multimeter, and then you recorded the temperature. Now, we're all human. There's going to be a delay there. But in this setup, you put the sensor in and then connect the leads to the dry block and let it run through the switch test. And when it runs through the switch test, it captures those values all on its own. That is one of the biggest time-saving features used in industrial applications. That way the technician can be off deployed doing something else. We've added in the capability of reading sensors under test. So if you look at this particular calibrator, you can actually see that you can plug in thermocouples, RTDs, transmitters, everything right in the front. And then because you can do that, you can do standalone work orders. You can run software that allows you to capture results and save those results. So once you do that, you can generate certificates, you can save history, you can actually watch history. RTDs will shift over time. You can actually watch that, and you can do predictive maintenance and say, well, I think this is going to fail within the next 3 months based on what I'm seeing in this indication, so you can prepare for that. So all those features make this more valuable than it even was before. Sorry about that. I kind of hopped past the slide. So we've got convertible models as well. So now we said, okay, we've got the dry blocks that do what the dry blocks do, but we've got customers that have liquid and glass thermometers. And We've got customers that have odd shaped sensors, and then we've got the pharmaceutical and food market that have clamp sensors. And some of those we just can't accommodate in the dry blocks. So what do? Well, we've got a couple of models that are available. We actually have 3 of them now that are available to do liquid or dry calibrations. It makes it very convenient for a user, especially if they've got a lab. They can switch from dry to wet operation as needed. And one of our newest innovations is we've got a model now that uses this kind of setup here, and specifically this part here. That's a canister. So whereas with a dry block that's wet or dry, you have to pour the fluid out, clean up the well, then drop the insert in. With this setup, you just pull that canister in and out. That canister holds the fluid. You put it in the well when you want to do a wet calibration. You close the top, take it out of the well when you want to do a dry calibration. That makes for a very quick cleanup for that customer. Very efficient. So these are going to become important as I talk about the different sensors that we can accommodate and what we can accommodate. So when we talk about the ones for sensor types and concerns that we can accommodate, the first 2 big ones that we're going to talk about are glass thermometers and contact sensors. So glass thermometers will have a change in diameter throughout the length. Okay, there's typically going to be a reservoir of fluid that's got a larger diameter than the length of the thermometer. You can't read the scale while it's in the dry block, so that presents a problem because you got to pull it out where now it's going to experience a difference in temperature, and then you got to put it back in. So you've got a stability issue there. And glass can be very fragile. So you start to pull out a glass thermometer and kind of slips a little bit, and it can shatter right there in the dry block insert. So glass thermometers are just not a good fit for a dry block application. That's where you would want to go to the convertible model. And contact sensors, you can't immerse those in a dry block, so they can't be tested as a standard probe. So those would not be suitable for calibration in a dry block. So what do we see as typical sensors? So we talked about the bimetallic. So we'll typically see bimetallic thermometers, wet bulb sensors, RTDs, thermocouples, thermistors, and switches. And you're going to do different readings for those. So as we talked about very early on for the bimetallic, you're going to read the dial. Wet bulbs, you might be looking for a dial indication or a function. RTDs, you're looking for a change in resistance. Thermocouples, change in voltage. Thermistors, change in resistance. And switches would be a change in continuity across the switch as it changes state. Now, some sensors that are going to kind of require special attention, right? So larger diameter sensors, again, everything's trying to equalize. And the larger diameter sensors are going to require more energy and more time to stabilize. So it may cause additional, again, loading on that dry block. So you might need units with higher range or more energy. You don't want to have a large sensor and have that sensor require a temperature that's right at the edge of what that dry block can do. Because you may or may not have the energy to affect that and go to stabilization with that sensor. So it may require units with higher range or more energy available. And it's going to require careful monitoring. You're going to have to watch what is stable. And you may need additional time to ensure temperature equalization. You will need additional time through the sensor and get to stable reading. So in some of the more advanced dry blocks, what you can do if you're running an automated calibration is you can program in that additional stabilization time. And you can say, look, I don't want to know that you're stable until this part is stable. So it will check the stability of the dry block itself, but it will also check the stability of the sensor under test and say, yes, it's not changing within whatever time period and whatever temperature period you've added. So if you say, I don't want it to change more than a half a degree over the next 10 minutes, then you can set that stability criteria and it will not give you a stability indication until that happens. Long sensors. As we talked about in the single zone control part, long sensors act like a radiator, so they transfer that heat energy to ambient. The first thing you want to do, and this is actually a good practice for any use of dry blocks, is to minimize airflow in the vicinity. That's going to reduce the rate of heat transfer. Think about when you're trying to cool down a spoonful of soup. You blow on it to try to increase the airflow across it and cool it down more quickly. So you can insulate the exposed portion, and we'll talk about some insulation types of insulation a little later on. But you can also use a dry block with additional heat energy capacity to make up for that loss, or a deep well design, which might even be better, or a dry block with zone control, which is going to be the ultimate solution. That's all going to be beneficial for you if you're testing this kind of a sensor. Short sensors are definitely problematic, okay? If a sensor does not bottom in an insert, what you get is you get an air pocket, and that air pocket causes instability, and there's really no way to estimate accurately what the temperature difference is between the set temperature and what the temperature is at the bottom of that probe. You continue to get circulating air currents. It's not controlling by that depth in the well, so it's very problematic for a standard single zone dry block. The first thing you want to do is use a custom insert drilled to the length. So whatever the length of the immersion depth of that sensor is, that's what you want to have the insert drilled to. And use an external reference. So you can position that external reference at the same depth as the short sensor. And you can control using the external reference using our set follows true mode on the PTC and RTC series dry blocks. And do not leave airspace below the sensor. Again, that becomes very problematic. You really can't accurately determine what is happening in that well from one test to the next. Odd shape sensors. So sensors like this or this are going to be problematic for a dry block. Now, a dry block might be able to do this one here, depending on how long that stem is. That stem, you want it to be about 15 times the diameter of immersion depth. So you may or may not be able to achieve that. When we talk about beveled, we talk about changes in diameter. So this one here, we might be able to accommodate because we could just make the top of the insert larger. This one we might be able to accommodate, but it becomes very complex. This one, we're not going to be able to. So what you want to do is if you can remove these from the sheath material, that'll make them easier to calibrate. If not, this one is not going to be applicable for a dry block. The other ones we would have to make some very specialized inserts. And again, we can do some of that now that we couldn't do before because of the different machining techniques that are available. Sanitary sensors. Sanitary sensors are used in the food and pharmaceutical industries, and they're going to have this flange on there. And what that does is in those industries, you can't have a threaded in connection. What you have to have is a connection that clamps on. So those clamp sensors, they're going to have a flange on them, and the block or the insert design is going to depend on the diameter of the flange and how long the penetration length and what the diameter of the penetration length is. And I'll show you an example of how we might address that application on the next slide. Large heads. You might see these out in the field where a sensor is going to have a stem and then a large head. That becomes problematic if you want to do multiple sensors. It also is another source of heat loss. As that heats up, it's going to create more surface area and allow more transfer of energy to the ambient. And then things that are flexible, such as this, those become problematic for a dry block because you can't really situate them properly in a well. If you've got a small enough diameter, you can, but the larger ones are not going to work out so well. The other thing that you might see is we talked about sensors having the thermosensitive length at the bottom or having multiple thermozones. Those become problematic. You can use an external reference, but then you create airspace underneath the reference, and that becomes a problem. We've done some of those, but it requires testing to make sure that it's going to work appropriately and repeatable. So when we talk about the sanitary seals, we've got some specific models to address that. That application. We can do it dry or wet, but The specific concern is the penetration depth, so this part of the sensor or this part of the sensor. The flange size up here, because again, the flange sizes are going to create another heat transfer surface, and it's going to draw energy away from the block. The changes in diameter, so we've got one here that's got a change in diameter, which we can accommodate because it's smaller at the bottom and larger at the top. The flange weld, the tip shape, and the reference probe positioning. So what we do is we create special inserts that position. If you can look, if you can see this, we've got a reference probe hole right next to the holes for these sensors. So we can do these dry instead of doing them wet. These are pretty, this is a critical measurement in food and pharmaceutical for clean in place and for actual process movement. So you want to use the special insert. You want to get the proper calibrator for what they're trying to do and a flexible reference probe. That will address those concerns in a dry method. And ultimately, if we can't do it dry, we can do it wet. Multiple sensors, as the question was asked earlier, they can be accommodated. You're going to need a special insert drilled for all of them. You want to make sure you've got adequate clearance between the sensors, and they've got to be the same length. You can't have a short sensor and a long sensor in the same insert because even if you're using set follows true control, that set follows true control is only going to focus on one point. You're going to need an external reference in many cases just to make sure that you're reading properly at that level. And considerations for larger sensor heads have got to be taken into place. So like here, we've got a transition from a solid sheath to an electrical connection, and we've got to make sure we have that clearance available. You don't want to tilt or bend the probe inside the hole. And then going back to the stability and loading concerns, you want to use units with enough energy and units with onboard compensation to address those issues. So effective use of the dry block. Top of the line, they're burn hazards. Baths are burn hazards, but dry blocks are also burn hazards. And burns can be from hot or cold extremes. So if you have one of the ultra coolers that we make that goes down to -100, you can get burned from that as well. So what you want to do is know the status of the calibrator. Make sure you're looking at the display. Make sure you leave the display on until the calibrator is in a safe condition. The people around you don't know what you're doing with the calibrator, and they don't know if it's safe. And once you turn off that display, you don't know if it's safe. Use protection when possible. So here is a thermal shield. It's going to deflect airflow away from the top of the sensor and away from you if you're actually there. And be careful when you're removing inserts. We actually have some features on our new CTCs. There will be an icon right up here that will tell the user if it's safe to pull the insert out, if it's actually too hot or too cold to remove that time. And again, leave that display on until the calibrator is at a safe temperature. And I'm going to say that at least one more time in this presentation. So orientation. Dry blocks are not made to sit on their sides or on their backs. There's a couple of very small models that are made to be set up on a bale or set up on their end. But for the most part, dry blocks are meant to be set up in a perpendicular position to the surface. And the reason for that is airflow. If you look at the bottom of dry blocks, there's a space below there, and it's made for air to be able to be drawn in or blown out. And you don't want to block that airflow. So if you've got a couple of dry blocks sitting in a space, or if you got a dry block that you've got papers around it or things like that, make sure you've got clean airflow underneath that dry block so that that fan can operate as it's supposed to. Make sure that the ambient temperature is correct for ambient temperature and humidity for use of the dry block. And the one thing you will know is, going back to the Peltier element, those Peltier elements work on a differential to ambient. So if you get to a differential that the Peltier can't cover, you might be in a position where you can't reach a 0 point in that ambient condition. And what you'll see on data sheets is you're going to see a couple of different temperatures. It'll say that the calibrator has this capability at 0 degrees, this capability at 20 degrees, this capability at 40 degrees. So note that not all cooling calibrators will be able to reach that 0 point. And what you want to do is make sure you've got enough energy based on what you're going to do so that it will. Heat transfer fluids. Don't use heat transfer fluids or heat paste between the insert and the well, or between the sensor and the insert. The insert could become stuck. The sensor could become stuck. The heat paste solidify over time. Not a good idea in there because then you've got to replace that block. Fluid may contact electronics. Don't put fluid inside of an insert. The only time you want to consider fluid inside of an insert is with a manufacturer concurrence and training. Because of the tip design that we talked about on those sanitary seals, there are occasions because of the inconsistent machining that we do have to use a drop of heat transfer fluid in those inserts. That's the only practical example I can think of. Any other time, you don't want to put fluid in a dry block. The wells outside of the convertible units are not set up for that. And you could have fluid contact electronics, and that can cause a fire. When you select a dry block for use, you want to choose a dry block that's going to accommodate the sensor. It's going to have the proper range. So you might need 2 ranges with enough energy for the application, not right at the edge of the operating range, or that has inserts long enough. Required performance specifications. Maybe it needs an internal reference. Maybe you've got to have the external reference. Might need multiple zone control. Does it need load compensation? Or does it need process inputs? Those are all considerations for the task at hand. And inserts. Ensure that the insert is for the selected dry block. Make sure it's the proper material. Don't put the wrong material on a dry block. If you put a high temperature dry block insert in a low temperature dry block, it might be okay. You turn that the other way around and you'll melt the insert into the block, and that's not going to be okay. You've got to replace the block in that case. Plus, you've got to make sure that the diameter matches. So typically, a high temperature and a low temperature won't match exactly. You want to verify that the insert is properly drilled to accept the sensor under test. Check it at ambient. Don't get it in there at temperature and hope that it works. Make sure it works before you do the test. You may need a custom design. And you want to verify the condition of the insert. So you want to verify it's clean and it's not dented or scratched to prevent sticking in the well and sticking of the sensor under test. And it will also allow for proper heat transfer. So if you've got a very dirty insert, it's not going to work out well. Insulation. We talked about insulation for single zone blocks may be necessary. We've got some insulation here. They're in the form of plates. You would stack the plates up. But this is a better design. It's a ceramic type of material that is going to be encased in a tube. You drill out the middle for your sensor under test, and you cut it to length. It prevents that radiative effect and ensures that but you need to ensure that the insulation material is rated for the temperature, and ultimately zone control may be a better option. And stability. Readings should not be recorded unless the dry block is stable. Remember, temperature takes time. You may reach set temperature and range around it. It's going to seek stability. And the unit may have an indication and selectable criteria. So I talked about setting that longer stability for the bigger sensors. That might be available for you, and you're going to get the indication. So you might have a green check. You might have a check. You might have something else on the screen that shows that it's stable. And always believe your indications. Your initial response should be to believe that that block is at temperature if that's what the display says. This is an actual block picture of a 600-degree block. It will get very, very hot, and it's better to be safe than sorry. Hot and cold can burn, and proper handling of the precautions for the dry blocks and for the sensors. Be very careful. After use. If you've been above ambient, what you want to do is you want to cool the dry block down to an ambient temperature for safe removal of inserts and for storage. And if you've been below ambient, you want to take it to a boiling point to flash off moisture and then cool it back down to ambient. What happens is if you go below ambient, you're going to draw moisture out of the air. That can get on the surfaces of the block, the insert, and down in the insert. Any one of those areas can have a corrosion layer form. And once those layers form, you get different heat transfer and you can get probes or inserts stuck. So make sure you raise it to a boiling point, let it sit there for a couple minutes, and then bring it back down to ambient. And always remove your inserts. Ensure that they're safe to handle. Take them out of the block. Make sure they're dry. Clean them with a wire brush. You can use a minimal solvent, but make sure it's not a flammable solvent, or make sure that it completely evaporates. store them properly in the case, or use onboard block storage like we have in the picture there. You want to prevent corrosion or physical damage. So if you drop an insert, be very, very careful with it, putting it back in the block, because if it's deformed at all, it's not going to fit and it could get stuck. That's a big point. The big point about cooling the dry or heating up the dry block above boiling and then bringing it back down. Those are two big points in practical applications. Any questions? Sean, do we have anything in the chat?
No, there's no additional questions in the chat right now.
Okay.